Okay, so this is an outline of what we have covered throughout this semester. So we start with the OLS regressions, and we talk about its assumptions for the OLS estimator to be blue, which is the best linear unbiased estimator. And there are three conditions. First is that the shocks need to have zero mean. And second, that there are uncorrelated shocks, means that the errors are uncorrelated with each other. And the third is that the shocks have the same variance. And this is the Gauss-Markov theorem. And if you violate the first condition, you will have a biased and inconsistent estimator, which means that the expectation of your estimate is not the true parameter. And also it will not converge to the true parameter. If you violate the second one or the third one, then you still have unbiased estimator. However, it does not have the smallest variance, so it's not efficient. Okay. And we talk about some examples of how you could violate each of these three conditions, and also how you can test these three conditions. So we have gone through exercises of how to do them in Python. For heteroscedasticity, the third condition, that would be the Bruch-Pagan test. To test the correlated shocks would be the Durbin-Watson test, and to test the nonlinearity would be the reset test. Okay, and for each test, you can see in the class example what is the function to use and how to interpret the result. Okay, so that's the first part. And then that paves the way for the rest of the semester, where we talk through the extensions of the linear regression model. So the first subject is the panel data. So panel data is that when you have multiple individuals over multiple years, okay? And in the panel data model, you would have a linear regression. However, there are several kinds of variables, ones that are firm or individual specific. So that's the WI. The ones that are both vary by firm and vary by year, that's the SIT. And the ones that only varies by year, but the same for all the firms, that's the ZT. And then in the error term, you might have some variables that are firm specific, but you don't observe, and then that is the alpha I in the error term. And in this case, there are two scenarios, okay? The first one is when alpha I is correlated with SIT. Suppose we are interested in estimating the effect of SIT, which is the beta 2. And in the first scenario, alpha I correlated with SIT, then that would lead to bias. And we can correct for that bias using either fixed effect or first difference. For both of approaches, it would just be taking the difference so that we eliminate this alpha I term. And in particular for first difference, it is deducting the previous period's observation. For fixed effects, it's deducting the mean. Okay, so you need to know in the intuition of each of these methods and what kind of issue that they can solve. And also, of course, how to implement them in Python. And then the second scenario we're in is when alpha I is uncorrelated with SIT. And in that case, OS is still unbiased and consistent, but it's not efficient because of the correlated shocks. And in particular, all of these shocks have alpha I, so that for the same firm, the shocks will be correlated with each other. And there we could do the random effects to make the estimator blue again. And you have to remember, random effects does not fix the bias, okay? If you have a bias and alpha is correlated with your predictor variable, then you have to always use first difference or fixed effect, Okay, so that's the panel data. And the third topic we talk about is classification models, where you have the Y variable, the outcome variable is not a quantitative variable, but rather a categorical variable. So the first case is that there are two categories. And in that case, we would do logit or probit. And both of them you can think of, they are some transformation of the function so that you would have a function that is still increasing in beta x. However, it is bounded between 0 and 1. Okay, so your prediction from both logit and probit will always be between 0 and 1, and you can interpret your prediction as the predicted probability of being 1, whatever the category means. And to estimate that is using the maximum likelihood, okay? And then after estimation, to interpret the coefficients, you should calculate the marginal effects, which is beta times a PDF at beta x. So you should check the notes on that. And only that will tell you what is the change in Y for every unit change in X. Okay, so you always have to calculate the marginal effects. And in Python, you would have a function to do that. Okay, and also for logit, of course, there's also another interpretation using the odds ratio. Okay, so you should know that too. Okay, and then the second kind of classification model is when you have multiple categories, more than 2, but they are not ordered. And we give some examples. And in those cases, what you should do is multinomial logit, which is an extension of the basic logit. And then the third kind of models is when you have multiple categories, but they are ordered. Okay, so this would be, for example, the bound ratings, which you are working on in the final project. And in those cases, we should do ordered probit or ordered logit. And for all of this, you should know how to estimate these models in Python, and also how to interpret the results. And also for logit and probit, we also talk about how to estimate the standard errors using Bootstrap, right? If you want to test some hypotheses or construct the confidence intervals. Okay, so that's the third part. The fourth subject we talk about is non-parametric estimation. So this is when you have 2 variables or even more, and then the relationship between the outcome variable and the predictive variable is not linear, okay? So when it's linear, of course, you can just do linear regression, but when it's not linear, and there are several choices you could do. You could do machine learning, you could do polynomials, but the 2 models that we talk about, one is the kernel regression. For kernel regression, you have to understand what does the bandwidth mean, and how do we choose the bandwidth. So basically, kernel regression is just a weighted average of the Y value, okay, for some observations. And what's the weight you're going to choose, that's going to depend on the kernel. And if you have a wider bandwidth, then you are taking an average for those observations that are farther away from you. However, if you have a narrow bandwidth, then you are only taking an average of the values that's within that narrow bandwidth. So kernel function determines how the observations are weighted, and then your prediction would be a weighted average of the Y values. And to choose the optimal bandwidth, you would do cross-validation. Okay. And then the second class of model that we can use to do non-parametric estimation is the regression splines. And there we talk about first the basic regression spline. You basically split the range of X into several regions and using several cutoff points. And in each different range of X, you fit a different polynomial function. Okay, and then you need to make sure that after you connect all of these functions in every region of X, the final function would still be continuous. But then there's the question of how do we choose the cutoff points and how many degrees of the polynomials do we choose? And a systematic way to do that is the MARS, right? Which is through an iterative approach. In each step, you would add the functions that matter, that improves the prediction, and until the prediction doesn't improve as much when you add additional functions. And then you stop and do the pruning and cutting out the functions that do not matter as much. And for this part, we'll also talk about the quantile regression, which is estimating a different object, right? So here the object we are estimating is what is the quantile of y instead of the average y or the expected y. So the estimation of this regression is just to minimize the weighted distance to get the conditional quantile function. And then we also talk about how to interpret the results. So it's only the change in those quantiles. So the coefficient of some x tells you the effect of x on the quantiles of the distribution, but it's not necessarily on single individuals. Okay, and next topic that we covered is the survival analysis. So these models are for the case where you have the duration of something to be the outcome variable. And the problem there is that you have censoring, okay, which means that for some individuals, you only see a range of their outcome variable. So you, and for example, when you do a clinical trial and see when people die after taking that drug and how long do they live, and maybe people are still living today, right? They might die in the future. You don't know when they're gonna die in the future. And for those people, their duration is censored. You only know it's longer than something, but you don't know for sure how long it is. And when you have censoring and whatever you do, either to take the censored value or if you just throw out the censored people and run an LLS regression, you would get a biased result. And the thing you do here, the type of models is called the survival analysis. Okay, so we first talk about hazard function. So that's a way to describe the distribution of the duration. It maps one-to-one to the CDF and PDF of the distribution of the duration t. And then we talk about how to estimate the distribution of that duration. So remember the survival curve, which tells you how many people are still surviving, what percentage of the people are still surviving at each time. And it is a declining curve. And we can estimate that curve using these two non-parametric approaches. One is called the life table, which is taking the fixed intervals, or the Kaplan-Meier, which is using the actual event or death times. And those two methods will allow us to estimate the survival curve. But then if we want to know the effect of something on the survival curve or the survival rate, or if we want to use some X characteristics to predict the survival curve, And then we would have to estimate a more parametric model. So here we would have the Cox proportional hazard model. And then there are two ways to estimate it. One is the parametric approach. And you can estimate that using the maximum likelihood. And there you have to assume a parametric function, either the Weibo distribution or some other distribution. And the more common approach, more popular approach is the semi-parametric approach, where we calculate a partial likelihood. So that does not require any assumption on the lambda function. We would, because all of the hazard rates are proportional to each other. So we can just take the ratio and maximize the partial likelihood. So here, of course, you would also need to know how to estimate these models. And after we estimate these models, how do we interpret these results? And how do we generate our prediction and evaluate that prediction, okay? And for these several types of models, the way we evaluate the prediction is all different, right? So for linear regression or our non-parametric models, the way you evaluate in those cases, both the y variable is a continuous variable. So then you can just use the MSE, mean squared error. For logit and probit, the way you evaluate the fit of the model is the ROC curve, okay? And for the survival analysis, we have the concordance index, which is to take all the pairs and calculate for each pair whether we get it right or wrong, who lives longer. Okay. So all of these, so in the exam, you would both do a little bit of coding and also, more importantly, is to interpret the results and explain the intuition. All right. And the last part of the course, we talk about data visualization and how to collect the data. And for data visualization, we talk about what are the good design practices. And for data collection, we talk about web scraping, right? And also how to deal with the missing values. So there are several ways to do that. And then we also talk about censored and truncated data. So censored is what we've seen in the survival analysis. You have something, you only know a range, but not the exact value. And truncated data is that if it's in some range, and then you will have, you will miss those observations. And for both, you can re-estimate the data using the maximum likelihood, and that correct for those biases. And also throughout this semester, we also talk about some of the ways to deal with the issues in the data, right? In all of the examples, sometimes we would see a missing value and we would do some imputation. And we also do the Winsorizing to get rid of the outliers. So all of that you should know how to do too. Okay, so that's it.